Okay, here's our last one for dealing with Ka style problems. We've got 4 examples here. We'll take a look at them one by one here. I've already got them solved, so I'm really just going to discuss these since most of the time it takes to write out these ice tables is what's chewing up the time in the video. So I think we've seen enough examples if you've appropriately watched the previous vids. Here we're looking for the pH of a 0.01 molar carbonic acid solution. All right, so for that one then, what we want to do is just double check that carbonic acid isn't one of our 6 strong. Carbonic acid, as we look for it, ends up being one of our weaker acids, so we know this is going to form an equilibrium. So as we flip the page here, again, like in the last set of examples, usually at this point I'm getting fairly lenient with the entities method in acid-base chemistry because of this single proton theory, transfer theory with Bronsted-Lowry. So carbonic acid gives up its proton to water to create a hydrogen carbonate ion and some hydronium. Now all we were given was the initial concentration of our carbonic acid. We had nothing there. We're not given a pH. We're being asked to solve that one. So we complete the table much like we did in the last example. All right, we know that carbonic acid has to decrease in its concentration by a certain amount. Because of the 1-to-1 to 1-to-1 ratios, my products should increase by the same amount. And so I can predict some equilibrium concentrations. Unfortunately, they're a little bit sullied here by an unknown. We can get around that though once we start doing our equilibrium law expression. Ka is given here, and we can start filling this one out. The only big difference between this one and the last one is the question didn't give us the Ka, but because carbonic acid is on our data sheet, the data sheet does tell us a Ka value. Remember, this last part here is the lists of your Kas. So if a question appears to be missing some information, especially a Ka value to solve these pH problems, look on your data sheet because it does give it to us there. So that allows us to put in the Ka. We can fill out our equilibrium expressions. There's your x squared, 0.010 for carbonic, but then we make our assumption. X should be small enough that it is safe to ignore. If you wish, there's the rule of 1,000 to check, and if I divide this incredibly small number into 0.10, I get a value much greater than 1,000, which means the amount of change in my initial concentration is insignificant. So this one is safe to do. Run it through then, and X will work out to 6.71 and some change. Put in that unrounded value into your pH negative log formula, and we get a value of 4.17. Okay, so we are doing this ignore X strategy when solving for pH. And it will work out to roundable, accurate answers. For question number 2 then, we're going to do the pH for a 2 mole per liter hydrofluoric acid solution, fairly highly concentrated. Okay, let's see if everything still works out in this particular case. So, again, there's your single proton transfer. Hydrofluoric acid is one of our weak acids. All right, fairly strong. The Ka is given, 6.3 to the negative 4. And so it would donate its proton to water, creating fluoride ion and hydronium in its wake. We can see the initial concentrations. 2.0 is given to us in the question, starting from 0 for our products, because how do I have these things before I dissolve the acid? I don't really know. We can see the 1-to-1 to 1-to-1 changes. Hydrofluoric acid has to decrease, while fluoride and hydronium increase. And so we get these as our equilibrium concentrations. We go now to our equilibrium law expression. All right, there we go. Products over reactants. No exponents because of the 1-to-1 ratios. And then I plunk in my numbers. All right, 6.3 came from the data sheet. X squared, there's my 2.0 minus x, but I'm going to use the strategy of ignore x here for my acid ice tables. I can check if you're nervous about doing this. Remember, it's just the acid concentration divided by the Ka. If it's greater than 1,000, it all works out. And so you can see here that it does work out to a value greater than 1,000. So ignoring x is valid. We consider it to be insignificant, and we get an x value of 0.035. Now you just need to turn that into a pH. Works out to 1.45 after you round. Okay, so the ignore x strategy does allow us to get valid answers. I'll show you one more here. Okay, for number 3, calculate the pH of a weak or lowly concentrated hydrofluoric acid solution. We already know that hydrofluoric acid is weak acid. It's going to react partially with water, so we have the same equation as we go through. All right, so we have the same situation here. Ka is just equal to fluoride hydronium all over the hydrofluoric acid. 6.3 to the negative 4 is equal to x squared. We now just have that lesser concentration here at 0.1 minus x. We can check to see if it's safe to ignore. And if x is ignored, we get this answer. But when we check the rule, 159 is not greater than 1,000. This means that the amount of ionization is now significant compared to the 0.10 initial concentration. And so this one would require the quadratic to figure out. And we can see that we get a significant difference here in pHs. All right. So what we're going to be doing for your quizzes and tests, since we don't have this issue for the diploma exam, is we will be giving you questions in which this will always be greater than 1,000 for this unit, so you do have the ignore x strategy. Again, more realistic for university and going on, or if you're doing AP, you will be using the quadratic, percent ionization, or rule of 1,000 to validate any sort of shortcuts that you might want to do. Okay, so there we go. Take a look at the examples in 737 to 743. There's lots of good stuff there. They show the rule of 1,000 and explain it there with more examples in addition to mine. Try a few of these from 743, and there is extra Ka worksheets on D2L if you wish to get extra practice with this one. Okay, so you can see that this is the bulk of the calculations that we have for Chapter 16. All right, doing all these ice tables and the inclusion of all that Chem 20 pH, POH stuff. All right, get some practice in with this one. We have one last topic to get through, and that's just dealing with the base situations. They have one additional little complexity here, and it's one of those nitpicky things that Alberta Ed likes to do. You might notice that there is no Kb value for the conjugate bases. So we'll have to look at how we convert those in order to be able to do these same exact types of problems with basic solutions. All right, good luck, practice that. Expect the Kb videos to be up soon.